Hello, everyone. Welcome back for Chapter 8. In this session, we are going to take a look at this hypothesis testing, which is what everything we've done so far pretty much has been leading us to. So, the key concept, the basic idea for all of Chapter 8, we're going to take a look at the key components to do a formal hypothesis test. Okay? We're going to take a look at doing hypothesis tests on proportions, on means, and we'll talk about the possibility of doing these. While we won't directly perform tests in this course on standard deviations or variances, we'll talk about how it's possible. We'll actually do these and these. We'll actually perform hypothesis tests on population proportions and on population means. All right, so let's take a look at some terminology we're going to be using. We're going to be using this word right here, a hypothesis. So what does a hypothesis mean? Well, in statistics, the hypothesis is a claim or a statement made about a property of a population. So it could be a statement about a row, a population proportion. It could be a statement about a mean of a population. It could be a statement about a standard deviation or a variance of a population. So someone is going to make a claim or a statement about those. They're going to say that this is the value for rho, or this is the value for mu, or this is the value for sigma. And then we're going to come in and run a hypothesis test where we are going to test that claim. We're going to gather data and determine whether the data supports or fails to support the claim that has been made. These are also sometimes referred to as a test of significance, more commonly a hypothesis test. Okay? All right, so let's take a look at what's going on here. We'll take a look at an example here. So we have an example here where we have a recent study, and in that survey, 1,009 consumers were asked if they were comfortable having drones deliver their purchases. Right? Now, of those people, about 545 or 54% just about said, no, we're not comfortable with this. Right? Now, that value we just found represents a sample proportion. So we have an N of 1,009 because we talked to 1,009 people. We have an X of 545, and we have a P hat of about 54%, or as a decimal, 0.54. And so what we're saying is we gathered data, and here's what the data says. Okay? But this is sample data. And because we all know, you're bathed this far in stats, you know that when you sample, the value that you get from your sample, in this case, that 54% that we got from our sample, that's not necessarily going to be the same if we run this survey again, if we talk to a different group of 1,009 consumers. Right? But assuming that we've done things correctly, assuming that we did our sampling correctly, there was a simple random sample and all that business, the answer that we get if we ran this again should be pretty close to 54%, should be somewhere around there. Now, last chapter, what we said was, let's build a confidence interval around that 54% and hope that we capture the true population proportion. Right? So if we use rho or P to denote the proportion of consumers who are not comfortable with drone deliveries, that is the population statement, right? What we could argue from our data is that this proportion is greater than 1/2, or mathematically, P is greater than 0.5. Okay? That statement, that inequality statement about rho being greater than 0.5, is a statement about a population parameter. Okay? So in the big picture, what's going on here is we have a claim that is being made. We have a claim that the portion of people who believe that they are not comfortable with drone deliveries for their purchases is more than half. Okay? If I sample people, in this case 1,009 people, how many do I need? How many yeses to the statement would I need to get a significantly high number who are not comfortable with drone delivery? Okay? Let's say we ran this study again, and the next time we did it, we got this. Right? Well, if we think the reality, if we think the truth is that this should be about half of the people, then my sample is pretty close to that, and it's not a significantly high result. It kind of supports that the middle is 50, or that the population proportion is 50. If we ran it again a third time, and that time we got 1,006 people saying that they don't want drone delivery, that's 99.7, we would say, well, that, if the middle truly was 50%, that would be a significantly high result. So clearly, numbers close to the middle aren't significantly high. A number way over there, close to 1,000 or over 1,000, would be significantly high. But what about our data? Is that significant? And so what we're going to do is we're going to use something called a hypothesis test to determine that. Here's basically what's going to happen as a picture. Someone is going to make a claim about a population proportion or a population mean. They're going to make a claim that the value is this number right here. So this is going to be our claimed value. We're going to assume that that value is true. And we're going to build a sampling distribution around that claim. And we're going to say, if that value is true, our sampling distribution should look like this. And then we're going to go gather data. And then we're going to bring the data back, and we're going to map the data onto this graph right here. And if my data falls somewhere in here, close to the claimed value, we're going to say something along the lines of, yeah, it looks like the data supports the claim. But if our data falls over here, significantly low, or potentially over here, significantly high, if we're way down here somewhere, or way up here somewhere, we're going to say that our data doesn't really support that claimed value. And that's the nutshell of hypothesis testing. Where the math comes in is here. Things that are way out here are obvious. Things that are really close to here are obvious. But how far away do you have to get before you're far enough away to be considered significantly low or significantly high? Right. Now, the way that we're going to measure that, how far away you have to be, is we're going to use something we're going to call significance. Because hypothesis tests are also called tests for significance, and we use probabilities to determine that significantly low or significantly high, then the significance of the test is what's going to be used to set those cutoff values. Right? All right, so let's take a look at some more terminology that's going to show up. You're going to see hypotheses come in two flavors. There's going to be the null hypothesis, and there's going to be the alternate or the alternative hypothesis. The null hypothesis is almost always denoted by H sub 0, H naught. Okay? The null hypothesis is a statement about the value of that population parameter, whether it be a proportion, a mean, or a standard deviation. And it is a statement that says the population parameter is equal to some claimed value. So a null hypothesis is a statement of equality about a population parameter. The alternate or the alternative hypothesis, and you'll sometimes see it H sub 1, you'll sometimes see it H sub lowercase a or sub capital A, the alternate or the alternative hypothesis, right, is a statement that that parameter, whether it be the proportion, the mean, or the standard deviation, has a value that differs from the null hypothesis. Right? The null and the alternative are complements of each other. So when we state these hypotheses, we write them so that they are complements. The alternative will contain inequalities. The null contains equality. Okay? Because we want to have a scenario where only one of these two things can be true, we write our hypotheses so that if one is false, the other must be true. There's no gray space. There's either this one's true or that one's true. They both can't be true, and at least one of them must be true. Okay. When we're writing our hypotheses, to prepare for the hypothesis test, when we're writing our hypotheses, we find the claim that is made in the statement about a population parameter. That claim will be one of these 6 statements down here. Once we find which one is the claim, we then write its corresponding pair, its complement. Now I know that at least one of you is out there thinking, hey, wait a second, those aren't complements. Those aren't complements. This is the only one that's actually a complement. If I'm saying that mu is bigger than k, the complement should be that mu is less than or equal to k. If I'm saying that the mean is bigger than 5, the complement should be that the mean is not bigger than 5, less than or equal to 5. And I agree with you. Okay, one of the weird things that happens, and it depends on who writes the textbook for stats. The author of this book, Triola, chose to pair up his hypotheses as you see them on the screen. And so I am honoring his choice and having my notes be that way, and the questions will be that way, and the homework will be that way. But just be aware that this first pair of hypotheses might be written this way by a different instructor. Oops. Because when we write them like I just did in green down here, these two statements are truly complements. One says you're k or smaller, the other one says you're bigger than k. So if you think of a number line, if there's k, the null hypothesis includes k and everything smaller. The alternative hypothesis then just includes everything bigger. And so it would cover the entire number line, truly complements. For whatever reason, and I've had many conversations with other stats people about this, some stats instructors, while they tell you that the two claims are complements, they choose not to write them that way. And I can't give you a logical explanation for why. Right? Now, the pair of hypotheses that we choose, whether it's, I'm going to call them 1, 2, or 3, depends on the claim that was made in the statement. But regardless of which pair of hypotheses you end up with, when we test, and this is step 3 here, when we test, we assume that this is true. We assume that equality is true unless we can find enough evidence to say it's not true. Okay? All right. This is really tricky, so let's take a look at a couple examples of writing hypotheses. All right, so I'm going to read this first one. A school publicized that the proportion of its students who are involved in at least one extracurricular activity is 61%. So the claim or the statement being made here is about a population proportion, that is the proportion of its students, so rho, is equal to, because they're saying it is, 61%. So since the claim contains equality, the claim is going to be our null hypothesis. So our null hypothesis is that rho equals 0.61. Our alternative hypothesis then is that rho is not equal to 0.61. I have a claim about equality. It is exactly. I have the alternate that says, no, it's not that. And then we'll go gather data, and we'll see if our data supports the claim or if it provides enough evidence to reject the claim. Okay? So this is a claim about a population proportion, so I'm using rows or p's here, whichever you want to use. All right, let's take a look at number 2. In number 2, a car dealership announces that the mean time for an oil change is less than 15 minutes. So we have a claim here. The claim is about the mean. So the mean, the population mean, is less than 15 minutes. Okay. Since our claim is a statement of inequality, a strict inequality, our claim is going to be the alternate hypothesis. Our alternate hypothesis then is going to be that the mean is less than 15 minutes. Our null would then be that the mean is equal to 15 minutes, or if you prefer, the mean is greater than or equal to 15 minutes. And then we're going to go gather some data, and we're going to check the mean time that it takes for an oil change. And we're going to say, hey, does the data support the claim that it's less than 15 minutes? Or does the data not support that claim? All right, let's take a look at number 3. A company makes an advertisement, and their advertisement says that the mean life of its furnace is more than 18 years. So I've got a claim. My claim is that the mean is more than 18 years. Now, just like in the last one, our claim is a statement of strict inequality. Since it does not contain equality, it's going to be our alternate hypothesis, that the mean is greater than 18, which makes our null hypothesis the statement that the mean is equal to 18. And then we're going to go gather some data about these furnaces. We're going to measure how long they last. And we're going to say, hey, does the data support, or does the data fail to support what's going on here? Okay. Now, no matter what hypothesis represents the claim, we always begin our hypothesis test by assuming that the equality condition in the null hypothesis is true. So in the last example there, even though the claim was about them lasting longer than 18 years, we're going to start by assuming that 18 years is the mean, and that they don't last longer than 18, they just last 18. So then I'm going to test. And when I perform the hypothesis test, the mathematical answer, the math answer, is either going to be reject the null hypothesis or fail to reject the null hypothesis. We are either going to have enough evidence to reject the null hypothesis, that that statement of equality is not true, or we're not going to have enough evidence. The evidence will fail to reject the null hypothesis. Now, because we are making our decision based on a data set that is a sample, there's a possibility that we could make the wrong decision. That is, there's the possibility that the answer that we give could be wrong. Whether the answer is to reject the null hypothesis or to fail to reject the null hypothesis, it could be wrong. And those errors that we get from this, the potential errors here that we're looking at, we refer to them as a type 1 error and a type 2 error. A type 1 error occurs if the null hypothesis, the type 1 error occurs if the null hypothesis is rejected when it's true. So a type 1 error is when you reject it when it's true. A type 2 error is when you don't reject it when it was false. Right? So if you think about this in terms of like a tree diagram, right? The null could be true. The null could be false. That's reality. Then we run a test. Well, we could reject, or we could fail to reject. And down here on the other branches, we could reject, or we could fail to reject. Okay? Now, both of those branches are just the only two possible answers we can ever get. We want this to happen, and we want, oops, I did that backwards, sorry, let me fix that. We want this to happen, and we also want this to happen. Those two branches of that tree diagram are correct responses. If the null is true, the top branch, we want to fail to reject it because it's true. We shouldn't reject it if it's true. If the null is false, the bottom branch, we want to reject it because if you think it's false, if it is false, then you should reject it. These two branches, the one that goes up here, oops, the one that goes up here and the one that goes down here, those are possible test results, but they're both wrong. Okay. This is the type 1 error up here when we reject, but we shouldn't. And this is the type 2 error down here, which is when we reject, but we shouldn't. What does that mean? Well, it means that I might make a mistake. I might make a mistake when I run this test. And I just have to acknowledge that in the real world, there is never going to be a test that says it's absolutely 100% accurate all the time. You're always going to get these errors slipping in, the type 1 errors and the type 2 errors. This is sometimes referred to as an alpha error, and this is sometimes referred to as a beta error. Alpha and beta errors, type 1 errors and type 2 errors. Depends on who wrote the book, what they call them. Okay. Ideally, in a perfect world, you'd try to make them both small, but there's this weird quirk that happens in the math. If you make one of them small, it makes the other one big. If you try to reduce the number of type 1 errors, it is going to increase the number of type 2 errors. And if you try to reduce the number of type 2 errors, it increases the number of type 1 errors. It's just this weird thing that happens with the math. Okay. All right, we're looking at about 24 minutes right now, so I'm going to stop this video here, and we'll come back and pick up from there. We'll take a look at an example of type 1 and type 2 errors. We'll talk about significance level, and we'll start building tests. So I'll see you all back here for part 2.